good to officially
Thanks for coming. I'm Lloyd, one of the co-organizers of GG Twin Cities. Thanks so much for coming out today on this first weekend in February. Do a quick introduction of other co-organizers. We've got Patrick Fuentes over here, Stephen Fluin, Stephanie Trimble, and Jeff Williams somewhere. He's running around making sure everything works. So we're kind of the general organizers of GG Twin Cities. We have our meetup every month throughout the year. And this event really warms my heart in a pretty awesome way. So I'm glad everybody could come out. This really for me is kind of the representative event of the GG Twin Cities. I had signed up to help organize this group, this meetup at Google I/O one year, a few years ago. And thinking that the Google I/O is this conference in San Francisco where there's so many sessions throughout the day that I found myself getting anxious because I wanted to be in many places at one time. And I wanted to bring that excitement back to the Twin Cities. And there's a lot of great tech talent here. And I think this event really nails that feeling that I'm trying to get throughout the day, or that we're all trying to get. Throughout the day, there's going to be so many sessions, hopefully, that you can't quite figure out where you want to be because you want to be in multiple places at once. And also, look around. All of these folks here it's a little bit self-selecting. You're taking your Saturday to come learn about something new, to further your career or your education. So this is a pretty good selection of folks to get to know. So be sure you meet somebody you haven't met. Thank our sponsors who make this event happen. We'll call them out here in a sec. So, actually, I think that's my turning it over to Stephanie. So.
Hey everyone, just a couple of thank yous. Of course, thank you to Google. Without them, we can't make this event happen. Target, they are one of our premier sponsors. Thank them at the after party. They're hosting that. The Nerdery, thank you for hosting the wonderful breakfast this morning. If you want to come up and say something while I announce the other sponsors, that'd be awesome. In here. Thank you to Augusto and Livefront. They are partner sponsors for the third year in a row now. And then another thank you to MentorMate and Iron Yard. Also, MentorMate is our media sponsor, so make sure you check them out on Periscope. And then the USD, of course, for providing this awesome venue to us as a sponsor. Make sure you use the hashtag DevFestMN all day today. And I will let the Nerdery come up and say something.
Thank you so much for everyone who organized it. Lloyd, Stephanie, especially this guy right here, Patrick Fuentes. He's a total rock star. Stay away, recruiters. Pretty strong underneath this. Thank you so much for the community. I'm so proud of the Minnesota community. You guys are awesome, and thanks for having us.
Thank you. Big round of applause for our sponsors. Thank you.
All right, I'm going to do some really quick announcements before we kick things off here. So last year we only had 5 rooms, tracks. This year we expanded that to 6 rooms. So we've got this auditorium, we've got the small auditorium on this floor, and then there's another 4 rooms up on the 3rd floor. So lots of amazing content today. If you are looking for any information about what's going on, DevFestMN is the website. Should hopefully work on mobile, depending on when it is pushed. We are also have a great app on the Google Play Store, and then we also this year are trying something new with a Slack team. So everyone that is attending should have gotten an invite. Feel free to have a conversation and ping us if you need us on there. The Wi-Fi is UST guest, UST open, and it does not require any sort of password, so you should just be able to click on the yes, I agree to all of your crazy terms and conditions. All the sessions are about 50 minutes or less, including QA, and we're planning on having about 10 minutes for you to move between sessions each time. Lunch is at noon, and then we're going to have a closing notes at 5 p.m. How many people were here last year? Okay, a lot of you. The closing notes will be quicker this year. We are doing giveaways again, not the same quantity, but we have some great prizes like a Pixel C and things like that. We're going to be doing it based on 3 things: session feedback, photos, and the overall survey at the end of the event. same as last year. If you are interested in the photo contest, we'll announce more details in the #photos channel in Slack, which anyone should be able to join. And if you need any help, ask someone in a green shirt and we'd be happy to help, or ping us on Slack as well.
I'll be super brief. I was just lucky enough the other organizers said I could introduce our keynote speaker today. Lloyd was talking about Google I/O, a really inspiring event that we've all attended. When I've gone to Google I/O, one of the speakers that I've loved to watch, Chet Haase, has been kind enough to come out and join us today. I'd like to point out something that not a lot of people know. Chet is a prolific advocate of the Android platform. So much so that a lot of people think he's on the developer relations team. He's a framework engineer that's like actually making Google work. So again, huge thanks for taking the time away from writing the code that I write code on top of to come and give a keynote. Everyone, a warm round of applause for Chet Haase. Thank you. You may want to hold that till the end. You don't know what I'm going to say. I don't think I'm talking about that, so I don't know how to get this. Or I could talk about that instead. All right, so when Patrick asked me to come and speak at DevFest, I'm pretty sure he expected me to say no, and usually I do. But it turns out I really like going to Minnesota, so I took it as an excuse to come here and join you and talk about Android. And that's where it kind of broke down for me. I thought, well, this is a general Google developer audience. I'm really not going to talk about general Google things. I'm going to talk about Android because that's the stuff that we work on. And frankly, that's all I know how to talk about. So first of all, it'd be good to find out how many Android developers are in the audience. Okay, so maybe about half. Maybe if we could just, if everybody could get up and then move to one side, maybe the Android developers could go up there. Actually, there was more Android. Okay, Android developers down here, everybody else up there. Okay, just stay where you are, and I'll try to speak to all parts of the room, and everybody else, you can just take a nap. I wanted to talk about mobile development in general. It's targeted at constraints of Android, but it's sort of general problems that we have in mobile that particularly people that have come from other development spaces may not really be thinking of to the extent that they should. In particular, if you come to Android as a Java developer, you're like, I know this language, I can totally rock on this. And then you bring over the patterns and the libraries and approaches they do have in server and desktop environments that may not actually work very well for your app. So I wanted to talk about some of the constraints of mobile development today in general, specifically about Android, not getting too deep in the weeds there. So I wanted to start. This is going to work for me. Here we go. Excellent. On there, thank you for inviting me. It is always fun to come to Minnesota. I like coming here. In particular, it gives me an opportunity to see some of the nice things in Minnesota again, like some of the nice art and natural wildlife. That's always good. I also really enjoy the largest mosquitoes I've ever seen. And it's fun to come to Minnesota to enjoy the commerce, which is pretty good, really. Okay, so let's talk about Android, where we're at right now. So lots of new platforms and new form factors in the last couple of years. Obviously, everybody's familiar with the Android phone. In the meantime, we have Android Wear, all the mobile or the wearable stuff coming out. Something like 4,000 apps and a whole bunch of watch faces. Who knew that people actually wanted to tell the time on their watches? Android TV has come out. We've got all kinds of apps coming out for that, as well as lots of new hardware coming online for people to watch and play these things on. Android Audio deals with car manufacturers, getting Android basically everywhere in your life where you wanted it. In the meantime, lots of numbers. So the growth of the platform is so explosive, it's a little bit hard to get your head around how the numbers work. So I thought I would try to break the numbers down for you. So as of last May, there were like 4,000 distinct devices. This doesn't mean 4,000 phones. It means like there's one of those phones and one of those phones and one of those phones and a tablet like that, and like over 4,000 things in the world. And that probably doesn't include all the ones that we don't even know about. So if we think of this in terms of like if there were 4,000 residents in a town, that would be about the size of Cannon Falls. Or maybe like, if anybody's familiar with Dundas, it would be like 3 Dundas, just full of distinct Android devices. It would be a weird town. But that's about the size if you want to measure it like that. Or if we think of it in terms of measuring units, it's basically the length of Hennepin Bridge plus the height at both ends, right? Pretty huge. Large numbers here. Let's talk about other large numbers. 1.4 billion 30-day actives. This basically says how many devices are actually active in the world. This is the number of Android users that are sort of checking in and using their devices in the last month or on a regular basis. That's a huge number. It's sort of hard to understand, so I think of it in terms of, well, if they were Twins fans, you could sell out like 36,000 games. That is a long season. If they were Lakes, then you could actually have about 120,000 minutes. And this, I should point out, this is using the real number of lakes, not the 10,000 they nobody cubic feet of water, if we want to measure it that way, then we could basically fill Lake Calhoun just with the number of 30-day active devices. Again, it's a little bit weird, but work with it. Right, so more numbers. Here's an even bigger number. 50 billion apps installed in 1 year alone as of last May. So if everybody on Earth had Android devices, wouldn't that be nice? That's like 7 apps per person. If we're only talking about Minnesota, that means everybody in Minnesota would have about 10,000, 9,000 apps, which is probably a little bit too much for memory constraints, but we'll get there. If we're talking about Faribault, it'd be like 90. I don't really know a device that would hold that many, but it's worth thinking about. Or if we measured it in terms of like 50 billion mosquitoes, then that could probably fill, I don't know, this room. So let's think about the mobile development model. Everybody sort of has a picture of how this thing should work. So first of all, you write the code, you produce this application, then you upload it to the Play Store, and then you make money. So it seems fairly straightforward. I'm pretty sure that's everyone's experience. And then we're all rich. If we look a little bit closer at the first part of that, it tends to look something a little more like this. So the question is, why? Why is it so difficult to write the app that gets up to the Play Store and makes the profit? And really, it's because of realistic constraints in mobile development in general. So I wanted to talk about some of those today. And in particular, I'll mention this a little bit later, but a lot of the ideas here were surfaced in a series of articles that we published on Medium.com that I would encourage every Android developer to go read. And this is the introduction section, which says, why do we have all these rules about how you develop on Android? Just so that you understand the context of this thing. And then you can better understand what those rules are and how you array them to write good apps. So one of the overall sort of big meta ideas and kind of a touchy-feely phrase is every device is a village. That means that everything on the device needs to share the same space and cooperate together to create a good experience for the user. Right? It's not every app for itself, which is a little bit more like this other sort of touchy-feely phrase, tragedy of the commons, where every app on the device is acting greedily in its own interests. Right? Maybe you think that your cat video sharing application is the only application that your user will ever want to use. And maybe you're right. Probably not. But maybe. Right? But chances are the user has other things to do on their device, including just going to the home screen or checking mail, or maybe also running the dog video sharing application that they have also installed. So if your application is greedily using all the resources it can, you have a huge heap, you're syncing all the time with the server, you're downloading all the stuff, you have a massive APK. You are using up resources that the user would really love to use for other applications and experiences on the device. And your application is making their overall experience suck a little bit more. Right? So what you want to do is make sure that your application is good enough for what it needs to be, but also contributes to a good overall device experience. Otherwise, they're just going to uninstall you anyway. So the user is going to decide whether you want to be there or not. So you really need to be a good citizen on the device so that they don't make the wrong decision for your application. So there are various aspects that contribute to these dynamics, so I'll walk through each of these. First of all, and this is the most important one, is memory. This really contributes to problems that we see across the board, whether it's performance or the size of the APKs or just the way the garbage collector behaves. But memory is really a lot more limited than you think it is. Right? So you may have a device in your pocket, you probably have a device in your pocket that has 2 gigs on it. Maybe it's an older device, a couple of years old, maybe it's 1 gig. It's okay, but you'd really like to upgrade and get a little bit more memory on that. The reality is there are still a lot of 512 meg devices in the world. Right? So you have users in emerging markets or users with older devices that have this very severely limited amount of memory on their devices, and your application should actually run on those because those represent a substantial portion of the Android market. Right? And one of the things that is really hard to wrap your head around is these aren't just the older devices. This isn't someone that bought a phone 4 years ago and they're really overdue for an upgrade. This is maybe someone that bought a phone last week. It was a very cheap phone because now the manufacturers can sell these devices with 512 megs on them for very cheap amounts of money. And that's really important in emerging markets where people don't really have the resources to buy the 2 gig devices or the new phones. Right? So your app is running on limited memory devices. It's important for you to actually develop and test for those situations. Another dynamic of memory is that the memory is shared. So all of these applications, this is the every device is a village concept. All the applications have to share that limited memory. And so when your application launches, if it's going to take up a lot of memory, then the system is going to go, well, this app needs a lot of memory. I have to go in the background and kill off the ones that are taking up the memory that it needs. So it's going to kill a bunch of tasks in the background. In really bad situations, it may even kill the launcher, so that then when the user leaves your application and goes out, then the launcher has to restart. Or maybe Gmail has to restart, or these other applications that the user wants to interact with frequently. Which means your application is going to launch, and then there's going to be a lot of jank because it's doing this stuff in the background so that it can launch yours, and then your application goes in the background. And then the system says, well, now I need memory. Hey, here's a really huge application. If I kill that one, I can get a lot of memory back. Right? So the more memory you take up, the more of the constrained and shared resources you're using. And the more likely it is you're going to cause bad situations for the user and specifically for your app as well. On the CPU side, it turns out that processors are a lot slower than you think they are. Especially if you're coming from the server environment where resources are kind of unlimited. You have this cloud thing where there's just tons and tons of cores and machines, and threads thrown at the problem. Well, you have a CPU. If you're lucky, you have 2, maybe 4 cores. Some of the new devices have more than that. But one of the things that is a little hard to understand from the outside is even if there are multiple cores on the device, and even if some of those are relatively fast, certainly faster than they used to be, they are not running at that speed all the time. So Android will constantly throttle these CPUs to make sure that we're not burning the battery. I don't know if you've ever run like a really intense 3D game or a VR thing or whatever, and the phone gets really hot and the battery really cranks down. It's because those kinds of things really do use the CPU very intensely, CPU and GPU. And in doing that, they run the battery down. Well, you don't want the user's battery to die in a half hour, so Android works really hard at making sure that CPUs go into a very low frequency idle mode most of the time. So when there's user interactions or when there's animations or graphics that need to happen that require higher CPU resources, then we spin the chip up. But most of the time it's actually running at a slower rate. So even if you think the CPU is fast enough, chances are it's running a lot slower than you think it should, simply because that's the dynamic of actually making sure that the device can actually stay alive all day. On the GPU side, a lot of similar dynamics in terms of performance, in terms of throttling as well, throttling both the GPU as well as the bus, carrying stuff from the CPU to the GPU. It's cranked down a lot. Also, texture uploads are expensive, so the more interaction you're doing with bitmaps or things that generate bitmaps, like text and path drawing, all the stuff creates bitmaps and then we upload it to the GPU. The more of that you're doing, the more expensive that is and the more time it takes, just because this is an expensive part of that whole pipeline getting to the GPU. Also, another dynamic on GPUs is fill rate versus density. So over time, these screens are getting amazing. I find it incredible that you got a phone about this big with a 1080p video on it. I have no idea why. I don't need that kind of resolution. I'm happy with less. But there are more and more pixels to fill, and the speed of the GPUs is not really keeping up with the fill rate. So if you think about it, this is my favorite thing about graphics is it turns out X and Y, that's like 2 dimensions, right? So if you have twice the size screen, so you just like double in X and double in Y, that's 4 times the amount of pixels that we have to fill. right? Because it's follow me here, 2 times 2. So that's a lot of pixels to fill. And in the meantime, the GPU, I bet, didn't get 4 times faster. So we're working really hard to do things as quickly and efficiently as possible at the framework layer. But in the meantime, if you're asking us to do far too much, then it's a real problem. One of the things that kicks in is overdraw. I don't know if anybody has used the tools that we have on the platform to make sure that you're not drawing things too often, but you should. Right? So there's a common situation where somebody will, for very valid reasons, they'll have a window background, and then on top of that, they've got a container with an opaque background, and then on top of that, they have a list view with its own background, and then the list view is filled with items, each of which have their own background, and then there's some text in the list view. So let's count. We have a window background, a container background, a list view background, item backgrounds, and then some text. Right? So that's 5 times. The pixels that are actually inside the text are being drawn 5 times. Right? And only one of those did you actually see. The user actually only saw the pixel that's in the text because that overdrew all the rest of the stuff that we wasted time drawing. And we try hard in the framework to eliminate some of that stuff, but in the general case we can't. So we depend on you, the developers, to do the right thing, to actually run the tools and say, oh, I'm doing overdraw here, I have an opaque container that's completely covering another container, maybe I should eliminate one of those backgrounds so that I'm not telling the hardware to do too much work all the time. Fill all of these 1080p pixels. So memory equals performance. I sort of alluded to this over time, but not only is memory constrained, but the dynamics of how we allocate and collect that memory contribute to performance problems. One of those is in the way that we have these shared task spaces where when you launch, we have to kill other stuff in the background to make room for your cat video sharing thing. But that means that we're doing a lot of work in the background, and we're going to do a lot more work when you go in the background. We need to allocate memory for another application, right? So the more memory that's being consumed, the more work the garbage collector is doing, the more work the task manager is doing, just to keep up with all the memory processing that needs to happen in the very constrained environment in which we're living. So that's the task thrashing part of it. There's also slower allocation, so the larger heap that you have, the more information we need to walk through in the runtime to actually figure out where to put these things. Right? And then the heap gets fragmented over time, and we have to walk further and further down this very large heap to do that. We have slower collections, again, because there's simply more to walk through each time. There's more things that are still being referred to or not being referred to anymore. We have to go free, and the larger the heap is, the more work that is, and the slower it is to do that, the more time it takes. And then finally, just more garbage collector activity in general. Every time you're allocating these temporary objects, we're allocating the things, we're freeing the things to make room for them, on and on and on every frame. Possibly causing jank or interruptions during operation, which you really want to avoid. It seems worth going over some of the technical details of how the garbage collector works so you understand this. And there's differences between Dalvik and ART, so I'll cover some of those. I stole these slides from the garbage collector team. I think the squigglies stand for threads. I'm not sure. It's not the most attractive slides in the world because I think they're busy actually writing garbage collectors, which I would really prefer they spend their time on. So let's pretend you have a blue rectangle allocated. So you have a blue rectangle that comes in here and it looks at the heap and it says, so during the allocation phase it says where can I stick this thing, and then it goes ahead in the enumeration phase and says here's a space for you, and it puts it on the heap. Then it marks things that are still being referred to or not being referred to anymore, and then it can collect the things like the red rectangle. Nobody's referring to that, so we can remove that, which makes space for another blue rectangle sometime in the future. Right, so now if we look at the details of pauses, this is where it starts to affect your application. So allocation phase, you're fine there, everything's running in parallel, but when we go to enumerate the heap and say now what things are referred to and not and where can we put this thing, we've got to take a pause in Dalvik, and it's a fairly substantial pause for some number of milliseconds while we figure out this information. Then there's the mark phase where we figure out whether things are being referred to or not so we know what to free in the heap. The mark phase can be done in parallel except for the second phase of that. So you do all this work and then at the end you say, okay, if anything else happened in the meantime, I need to pause the world there. So you've got these 2 pauses happening every time we go through and do any garbage collector activity on Dalvik. And then finally we free it at the end. On ART, we're better about the pauses. So there's no pause during the enumeration phase, that can happen in parallel. And the pause during the mark phase is smaller. So all that's good, still a little bit of pause there. But the one that you really want to avoid and the one that really kills you and causes jank in the system is what we call GC for alloc. This is a situation where you have a blue rectangle, and we see a space large enough for that at the top. All of that's good. So we stick it in there, and then another blue rectangle comes in. And if you look at the heap, you'll see we don't have space for it anywhere. We may overall have space for it in between the cracks, but we can't move stuff around to make space for it. So instead, we have to free something up to get a nice contiguous block that it can fit in. So that red rectangle has to be removed. Well, that means that we need to actually do the mark phase. We need to enumerate things, and we need to actually free that thing in order to make space for the blue rectangle. Right? So that means you're going to have a massive pause right in the middle of that, which is the GC for allocate pause. So we say we need to allocate, and we look at the heap and go, well, there's no space for it. I'm going to have to run a GC right now, and we stop the world so that we can do that for you. You will see this in the logs with the phrase GC for alloc. So if you are running an animation and you see some jitter there, and you just look at log count, you'll see possibly GC for allocs happening, and that probably means that you're doing a bunch of allocations on the fly. We're running out of space, and we're having to do a very expensive garbage collection operation on your behalf, synchronously freezing the UI thread and making it impossible for us to do anything until that memory can actually be allocated. It's worth pointing out, this is much better on ART than it was in Dalvik. Dalvik, you would typically get GC for alloc times of 20 to 30 milliseconds, which you're basically losing a frame or two just to the garbage collector process, not counting all the other stuff that you needed to do. In ART, that's a little bit more like 3 to 5 milliseconds, which is great, huge improvement. But 3 to 5 milliseconds is still up to about a third of the time that you have to render a frame. So you still don't want to take that on if you really don't have to. One of the best things that you can do for your application is run memory tools and make sure that you're not allocating on the fly in your inner loop or during an animation. Right? So if every frame during an animation you're doing something that allocates a bunch of temporary objects or is asking for a lot of memory and causing this thing to happen, eventually you're going to get a GC for alloc and you're going to freeze the screen in front of the user, which is a bad thing. It's worth pointing out that another way that ART got better in general and is more optimal than Dalvik is in the large object heap that it had. One of the problems with Dalvik is everything went into this one contiguous heap, including the little tiny temporary things and the long-lived large objects like bitmaps, which meant that it made it more expensive to sort of walk the entire heap and find room for things. It also made it trickier to find contiguous space for things you needed to stick in that heap, because there was this dynamic of just all kinds of different sized and lived objects in the heap. So now we have a set-aside large object heap that ART uses where we put the long-lived and very large stuff, and that makes it cheaper to walk both of those heaps into the GC. So that contributes to the slower pause times that we see in ART. Low-end devices, this is a good dynamic. As I pointed out before with memory, your device is really better than most of your users, and you should be aware of that when you're developing and testing. And it has more memory. And Moore's Law doesn't apply in the way that you think it does. So Moore's Law is still a thing. I don't know the exact magnitude of Moore's Law. Who does? Maybe Moore did. But things do get faster over time, right? So next year we'll be able to buy a phone that has faster CPU, that has more memory, that has faster GPU, bandwidth, whatever, right? 2 years it's going to be faster. You know, maybe there's some limit in the future, but in general things get faster. But that doesn't mean that A, the devices that users have today are going away because maybe they don't have money to buy a new device, or maybe it works good enough for them so they're going to continue using it. But the hidden one is, it also doesn't mean that the technology of today won't still be sold in 2 years. Right? So the fact that we're going to be able to produce devices that are much faster and better and cooler in 2 years means that the technology of today is going to be that much cheaper for manufacturers to package and sell at that time. So the thing that's selling today that is reasonably high-end, in 5 years will be very low-end and it'll still be sold somewhere. So if you're really looking at Moore's Law as the savior for your cat video sharing application, it's not going to save anything because there are going to be people that are going to be unable to run your application in 5 years because they're still getting devices that you thought were dead a long time. Smooth frame rate is a really important thing in general. If you're doing a lot of graphics or you're doing simple animations on the screen, anything needs to look smooth to the user. It's actually better to have a lower frame rate where you're only updating 30 times a second, but you're doing it consistently, than if you're running at 60 frames a second, most of the time, and then occasionally you freeze. One of the things that is not clear about this either is that there's not a smooth sliding scale when you take too long to draw. So in general, you're going to have 60 frames a second-ish to draw your stuff. That means you have 16 milliseconds on every frame to do everything. That's process input, that's process all the animation events, it's doing layout, hopefully you're not doing that in the middle of an animation. It's producing all the rendering commands that came out of the invalidations because of all that other stuff that happened. Then going into the native code and framework and producing the OpenGL commands that get sent out to the GPU and flipping the buffers. All of that has to happen within 60 milliseconds. If it doesn't, then we're going to pause for a frame. And the trick here is that it's not like if you take 1 extra millisecond, it's okay because at least we're going to display it in 17 milliseconds. Now we're going to skip an entire frame, which means that if you don't have 16 milliseconds, then the next time the user is going to see that input is going to be at the 32 millisecond mark. Right? So you're going to skip an entire frame, and they're going to wait that long. And it doesn't really seem like that much. 30 frames a second is decent, but it's the discontinuity that's the problem. Something is moving smoothly on the screen, and it pauses for 1 frame, and then it skips to where it should have been. They're going to see that. And if they see it a lot, it's going to be really disruptive. You want animations to be smooth, so you want your rendering to be as efficient as possible, and you want to do everything on the UI thread as quickly as you can so that we can keep updating the screen for the user all the time. Let's talk about runtimes. We referred to a little bit as before. Dalvik, that was the runtime up through KitKat, and then in the Lollipop release, Arc came online as the only runtime there. It's better, it's more optimal, there's fewer GC pauses and smaller GC pauses. All of that stuff is good. There's also better optimizations in Arc. We're able to do method profile instead of trace profiling. This is a big thing to people in the runtime community, apparently. It means that we can do optimizations on a much broader basis in Arc than we ever could in Dalvik. Dalvik is really constrained to run on incredibly low memory devices and in low memory situations, and it did its job really well. But then when the constraints widened a little bit, it really couldn't keep up. There were only so many optimizations that we could build onto the platform that it offered. So now we have the ARC platform instead, and we can do much more there. That's great, but obviously you still care about Dalvik for quite a while, because it turns out that ICS and Jelly Bean and KitKat are going to be able to work for a while. Hopefully not Jelly Bean. Anybody still developing? Or, sorry, Gingerbread. Anybody still doing Gingerbread development? Yay. Okay, and it's important to point this out. I gave a talk like this a few months ago, and someone said, so how does it impact you when company XYZ comes out with their new runtime specification with the new language thing? Like, that has, like the language that we use has nothing to do with the runtime, right? If they're optimizing a server runtime somewhere, then what does that have to do with my world? And I realize this may be confusing to people on the outside. That the language that we use, the Java programming language, is not the same as the Dalvik runtime or the R-time runtime, or certainly not the same as someone else's runtime that's not even running on Android devices. And it's also not the same as the hardware, so I wanted to give sort of a mental model of how these things work together in general on devices. So you have this top layer, that's the programming language that they're using to write this thing. It's the language that the APIs are written into, so you're calling into the view class, Java language syntax, all that stuff. That's all good. And then you're at the runtime layer where on Android we've got either Dalvik or Arc, depending on the device and the release. And then the hardware that it's actually running on, the Samsung device, the Nexus, whatever. In the server land, this is what it looks like. So you have the language, and then you have this server runtime, whatever that happens to be, and then you have this server thing. So we can think of some of these capabilities there. On the server runtime, you have, in general, a move-in compacting collector. That means that temporary allocations are very cheap. Right? They can, if you want to create a new rect object, that's great. They'll give you one of those, and they'll move it around as necessary. They'll get rid of it by moving pointers around. It's very efficient. They defragment the heap all the time. They're basically able to move objects around in the heap and quickly make space for new objects, as opposed to walking the entire heap and having GC for alley pods that we talked about earlier. In the meantime, they're running on server hardware, where the CPU, it turns out, is very fast. And the memory is essentially unlimited. Right? You've got the server farm out there. It can do whatever you want. Meanwhile, on Android, we have very similar Java programming language at the top, except we have two different runtimes there, which are quite a bit different. And then we have hardware that looks a little bit more like this. So in Dalvik, there's no compaction. So that means everything is allocated and stays on the heap. If we don't collect it, it's going to stay at the exact same place on the heap. So over time, your heap is going to get fragmented. And the blocks of contiguous memory are going to go down over time because we have these other things interleaving the heap all over the place. Just given the dynamics of how that runtime works, we cannot collect them. We can't move the things around on your behalf. So that makes it trickier to deal with memory in general and more necessary to make sure that you're actually freeing up the stuff that you don't actually need in your application or not over-allocating to begin with. On Arc, we actually do have compaction that happens at idle time. So when your activity goes into the background, at some point, Arc will decide that this is a good time to actually compact the heap so we can move stuff around so the next time your activity is in the foreground, we can work a little more efficiently with the heap. CPU, turns out, is a lot slower on these little tiny devices. And the memory, as we talked about before, is in general between 512 and 2 gig. That'll go up over time, but 512 will still be there for a while, longer than you want it to be. UI thread. The dynamic of the UI thread is basically everything that the user sees is going to be produced on a single thread. So the more stuff you do on that thread, the more chance you're going to have of causing jank or interruptions during animations or rendering, and then they're going to notice that thing on the screen. So in general, Android is a single-threaded UI system. That means that we handle the input, the animations, the layout, the rendering. All of that stuff is happening on a single thread for the most part. In the Lollipop release, we did come out with another thread. This is kind of an implementation detail. There's something called render thread, which is buried under the hood, where after we produce all the rendering commands, then we sync it over to the render thread, and that's actually responsible for talking to the GPU. We get a little bit of parallelism out of this. We have some animations, like the ripple animations, are able to run autonomously on this other thread, so they don't require as much sort of synchronous behavior between the UI thread and the render thread. But for the most part, it's essentially the same thing. We do all this stuff to produce the render commands, and then the render thread issues them to the GPU. So that means that everything you're doing on the UI thread could potentially stall that and cause a disruption for the user. Right? So if you decide in the middle of that, well, it's just a single web service call, it's not really going to be a problem. Actually, it will. Because you're going to call out there, you're going to wait for this thing to come back, and in the meantime, the user is waiting for the UI thread to do its work within 16 milliseconds. The window elapses, and they stall and notice the jank in your animation. So don't do stuff on that thread if you don't have to. There's lots of facilities available on the platform for you to avoid that problem, async tasks, loaders, whatever. Just make sure that you're doing the stuff that doesn't actually need to be on the UI thread on a different thread instead. Storage dynamics are interesting. It turns out that storage performance varies, especially if you imagine that a lot of the users, probably in emerging markets, may have a lot of their storage dependent on SSDs, SD cards, where the performance varies widely. Right? The performance is probably not as fast as the memory that's going to come bundled on the device to begin with, but also the performance per card can vary, and it tends to vary over time. So you really can't count on exactly the performance that you have on your device anymore, nor can you count on the exact size of it. Nor should you expect the user to always put their things on the internal memory of the device, because that expanded memory is really how they get their system to work. So they may have very limited memory bundled with the device, and then they have this SD card or external storage that they use for putting other stuff there. And you have to allow that as applications, because that's really how they make their lives on these limited devices work. So also your APK size matters, right? The larger, maybe you think it's much more efficient to bundle all these assets and come down with all these bitmaps, because then you don't have to fetch them from the server. In the meantime, maybe that APK is now too big for the user to fit on their system, and maybe they're going to evict it as soon as they want to install a different application. Network, again, yours is better than your users. I think here we tend to treat network and data capabilities essentially free. We have data plans, we have Wi-Fi all over the place. We spend all our lives in coffee shops anyway, they usually have Wi-Fi. But in the real world, they don't necessarily have access to that. 2G is really prevalent in other markets. And also, people tend to pay for their bandwidth, like on a per whatever byte basis. And it's really expensive to them. So a lot of times, they're actually operating offline constantly. So if your application is dependent upon a constant connection to the server, or if you really like to sync very often, your user will suffer, your application will suffer, because it's really not going to work in these situations. Right? So if you're constantly going out to the server and you can't find the server, and therefore the user can't see that they clicked the button because you were dependent upon this interaction, that's just dumb. You need to actually interact locally. You need to cache the operations, the actions of the user locally, so that if you're waiting on server feedback for some information, at least the user had a responsive UI. Or if the user is able to do something with your application without actually needing the assets being downloaded from the network, then make sure that that actually works on your application. And certainly don't oversync, because you may think that it's okay to just, every few minutes you check with the server, see if anything happened, but that is not possible in a world where people actually spend most of their time offline. So one thing to do about that is to actually test on slower networks, or test when there's no network at all, and make sure that your application can actually do the things that it needs to when it's actually disconnected from the network. So I'll come back to this point that every device, we have the choice to make it go like this, which is scary. Or we can make it interesting. Everything I talked about today is, most of this, not the Minnesota stuff. Everything else I talked about today came from the introduction article, which is called Understanding the Mobile Context. It's one of about 10 very long Medium articles. So I encourage you to go to Medium and check out the articles. You can absorb the understanding of mobile context. It'll sort of reiterate some of the stuff that we're talking about. There's also deep dive sections in memory, in CPU, in graphics, in UI thread, to sort of give you the deeper concepts and a lot more details that I didn't talk about today. So please, if you are an Android developer, and about half of you were, or maybe the rest were asleep, please read the articles, because we wrote this as a platform team. It actually came out of discussions internally at Google. We were at some meeting we'd gotten together with some app developers internally, and one of the app developers said, so whenever we come to the framework team and we say, we're doing the following thing in our application, you tell us not to do it that way. Yes, okay, yeah, I understand that dynamic, we say that a lot. Said, okay, great, so where's the stuff written down that actually tells us the way that we should be doing it instead? And it turns out it wasn't written down anywhere, it was just in our heads. Right? Maybe we just liked the attention. We wanted them to come to us just so that we could slap them down. Yeah. So we got together as a framework team and then the larger platform team and wrote down a lot of the stuff that we had seen over and over and over again from these apps. Not only the rules, but also the context of why the rules are really important. We put it all in these articles. I produced this massive doc internally at Google, and then when I put it on Medium, I think I exploded their word count, so then I broke it up into these 10 separate articles. So this comes directly from the platform team and is really intended for serious Android development, so please check out those articles. That is all I have. Thank you.
We have about 5 minutes for questions if you're good. I will try and run around. I don't know how fast I'll be.
So you were talking about how as the hardware is following along Moore's law, we still have to consider the stuff that's old. How does that affect the operating systems? Because you were talking about how Gingerbread is old and you hope no one's developing for it still.
Yep.
But that's that older hardware, because some of it can't run on iPod.
Right. So we have been working internally to make that more possible. So I think we had not obeyed some of these constraints on the platform level because there's sort of an expanding need to do more stuff all the time. So there were efforts starting in Jelly Bean about doing our stuff on a smaller basis, or maybe it was KitKat. Project Svelte. It was basically targeted at, okay, let's constrain all the stuff that we're trying to do so that we can actually have low-end devices that are being produced with more recent operating systems. There is still a tension there, but the general idea is that we should be able to have modern OSs even in these market situations. Yeah.
So you talked about different guidance that you can make applications better. You said it's in your head, and you put it in a blog right now. Are there different opinions or different guides in Google Android team which conflict with each other? Is there another person in Google says, oh, actually I don't agree with that. That's probably better to this way. Do you guys have a unified, standard way of thinking how to make things better, or there are different opinions and different guidance?
Are we all thinking the same way? Well, it depends on who you talk to. Did you actually want to use the word anonymous? So that tends to be a trigger one for this very issue, which is if you get too religious about any of the points in here, then it's a little bit silly because it really depends on the situation. So the one we come back to as kind of a religious trigger here is enums. So in the articles, I think the rule is avoid enums, and then we explain why. There's a lot more memory overhead for each of those classes. It's produced this runtime overhead about accessing the properties. In general, if you don't need all of that overhead, you should understand what the overhead is. However, there's a caveat, which is if you're using them in limited situations, if it's an application instead of a library that other people are using, if there's a very good reason for you to be using those enums, knock yourself out. I really don't care. What I do want is for developers to understand why we have that rule so that you can then make the right decision for your application. Right? And just to elaborate the point about libraries too, there's a big difference between you writing an application where you have a certain pattern of development and you don't use it that much that it's really causing the overhead problems that we're talking about, versus writing a library that everybody else is going to use and enforcing that behavior on all of them without knowing how they're going to use that. So we on the framework team work really, really hard at not doing things like that. We don't use enums internally in our most prevalently used APIs because there is a lot of overhead to them, so if we don't need to inflict that overhead on all the applications, then we should not. Right? Instead, we use really ugly, integer stuff, bit flags, whatever, because that will get the job done without the overhead, and then you don't suffer the next part. Yeah.
This might be a little too general, but I'm just curious, like, is there any best practices or common things to look out for to avoid the GC for alloc? Is it a lot of just instantiating a lot of objects, or what are some things that you've seen that are common reasons for that happening?
Yeah, don't allocate anything ever. Practice. I would say the most important thing to do is use the tools. One of my favorite unsung tools is allocation tracker. If you're on DDMS, or I don't know where it is in Android Studio these days, in the monitor application maybe, you can click the start allocations or start tracking button and then do a bunch of stuff and then click the get allocations. It'll tell you all of the memory that was allocated during those 2 points in time. It'll tell you the source code that allocated, the object that were allocated, the size. That's really important to use in situations where you really want to avoid allocations. I used that a lot when I was developing the animation framework that came out in the Honeycomb release, because I wanted to make sure that on every frame of the animation, we weren't doing something in the framework that would allocate a little bit of garbage along the way, and then eventually cause a GC for alloc in the middle of the animation. And it turns out we were allocating stuff. There's some hidden, actually, go read the articles anyway, but I really like some of the language stuff that is not obvious. It turns out that the JDK5 stuff where you have the for each syntax, which they call for each, even though it says for, I never understood. When you do a for, object this in this collection, it will allocate an iterator for you. It's just syntactic sugar around iterator and next, right? But it doesn't know whether that collection is empty, so it's going to allocate an iterator anyway. So it turns out that in the framework, on every single rendering frame, we had a for each syntax. It was allocating an iterator just to find out whether we wanted to send out a message to pre-raw listeners. And it turns out we never do. It's not a common thing for people to have pre-raw listeners hanging off that thing. So every single frame, we would allocate this thing just to see whether we could send out that event. And I found that through allocation tracker. So I would suggest that for your application. Figure out where the inner loops are, and try not to allocate during those. Figure out what are the things that are going to be run in every animation frame and avoid allocations there. It is the Java programming language. It's impossible to avoid allocations. I encourage you to allocate objects when it makes sense, but I also discourage you from allocating at times when pausing for GCs could really be a problem.
Let's have another big round of applause for Chet. About 9:51 right now. We've got 6 sessions starting in about 9 minutes. I also want to let everyone know that on the 3rd floor, the Google Cloud Spin team is here, and they have a really cool setup